Welcome back to the Deep Dive, part of the Neural Intel podcast. Today we're plunging into a topic that sits right at the intersection of really cutting-edge AI and, well, pure artistic magic.
Yeah.
The world of animation.
Mm-hmm.
When you think of your favorite cartoon or anime, you probably picture those incredible fluid motions, the vibrant colors, characters just bursting with life right before your eyes. It's, truly mesmerizing.
That's really it.
But what you might not often see is the hidden reality behind every single second of that animation. A monumental amount of incredibly repetitive and often, frankly, mind-numbingly labor-intensive work.
Oh, absolutely. It's a huge testament to human dedication, but it's also fundamentally a major bottleneck in the creative process.
And that's not just about the sheer volume of drawings, is it?
No, not at all. It's about the hours, the artist fatigue, the significant financial resources required to produce animation at scale. For decades, really, the animation industry has grappled with this challenge.
Yeah.
How do you maintain artistic quality while battling the relentless demands of a very manual production pipeline?
And that's precisely why we're taking a deep dive today into a groundbreaking new generative model, one that promises to fundamentally change all of that. It's called ToonComposer, and it's designed to dramatically streamline the animation pipeline. So our mission for you today is to unpack the truly impressive technical breakthroughs behind ToonComposer.
Right.
We're going to explore how it works, the ingenious engineering that makes it so effective, and the profound technical implications it holds for the future of cartoon and anime production.
Yeah, focusing on the core tech.
Exactly. Our focus, as always on the deep dive, will be squarely on the core architecture and the sophisticated mechanisms that make this technology so powerful. We'll be steering clear of the broader ethical or inclusivity discussions today. We're choosing instead to really dig into the engineering and the capabilities. And of course, to stay updated on the latest AI and ML research papers, remember to visit neuralintel.org and check us out on YouTube.
Definitely worth doing. We're all about those technical details here, and ToonComposer gives us a lot to discuss.
It certainly does.
Indeed. The core problem ToonComposer addresses is deeply embedded in the traditional animation process, particularly in what we call the post-keyframing stage.
Post-keyframing.
Right. So while the initial creative stages, where artists define the vision, that's where human talent truly shines. But the subsequent steps demand just immense manual effort. And this isn't merely a matter of time. It translates directly into significant resource costs. It creates a substantial economic and artistic challenge for studios worldwide.
So ToonComposer is aiming right at that challenge.
It sets its sights on tackling this head-on, yes.
Okay, so before we jump into the solution itself, it's always crucial to understand the why. To really appreciate the elegance and the impact of ToonComposers, we first need to understand those bottlenecks in traditional animation, and just as importantly, why previous attempts by AI to help out. Well, why they fell short.
That's an excellent starting point, yeah. The traditional cartoon production pipeline, whether we're talking classic Western animation or intricate Japanese anime, it's incredibly multi-staged and, as you noted, exceptionally labor-intensive.
Right.
It typically kicks off with keyframing. This is where the purest creative artistry resides. Artists meticulously draw the crucial defining poses and movements of characters and objects.
The anchor points.
Exactly. Think of them as the absolute anchor points of an action, the beginning, the peak of an action, maybe the end. If a character is jumping, the keyframes would be them crouching down, then mid-air at the highest point, and then landing.
That's where the vision comes alive.
Precisely. That's where the artistic vision truly comes to life on paper or, the digital canvas these days.
Okay, so those are the big expressive moments, the ones that convey the most. But what happens between those critical poses? That's where the real manual grind and the resource drain truly begins, isn't it?
That's exactly right. Following keyframing, you enter the notoriously laborious stage of inbetweening, often just called tweening.
Tweening, right.
This is the painstaking task of drawing all the intermediate frames that connect those keyframes, ensuring smooth, fluid motion.
So, like, if an arm is moving up.
Yeah, if our character is raising their arm from their side to above their head, the keyframes might be arm at the side, arm fully extended. Inbetweening involves creating every single frame in between those 2 points, potentially, 20 or 30 individual drawings, just to make that motion appear natural and seamless.
Wow. Hundreds of drawings for just seconds.
We're talking about generating hundreds, sometimes thousands of individual drawings just from mere seconds of animation. It's incredibly time-consuming. It requires immense precision to avoid things like boiling lines or flickering effects.
Yeah, that shaky look.
Exactly. And frankly, it's often quite repetitive and less creatively fulfilling for many artists compared to the keyframing stage.
I can imagine. And after all those frames are drawn, cleaned up, approved,
Yeah.
then comes the color. Right.
Yes. Then there's colorization. Each of those hundreds of in-between frames needs to be meticulously colored. And this isn't, a simple paint bucket fill process we might do on our computers.
No, it needs consistency.
It demands careful attention to detail, ensuring consistency in shading, highlights, textures, the overall color palette across every single frame. Imagine if a character's shirt color subtly shifted between frames, or a shadow appeared, then disappeared. It's visually jarring. So when you combine the demands of in-betweening, which is basically interpolation of form and colorization, interpolation of style and appearance, you can quickly see how the resource drain becomes astronomical.
So keyframing is creative peak.
Right. While keyframing allows for peak creativity, the subsequent in-betweening and colorization are largely mechanical, demanding this vast amount of human effort for tasks that are fundamentally about maintaining consistency and filling in the gaps.
Okay, so given such an obvious, costly bottleneck, it's really not surprising that AI has tried to step in before.
Not at all.
We've seen models like ToonCrafter, Anadoc, LVCD. They attempted to help out. But they didn't quite achieve the revolutionary shift the industry hoped for, did they?
No, they didn't quite get there.
What were their key technical limitations from an engineering perspective?
That's a crucial point to understand ToonComposer's leap forward. While those earlier AI-assisted methods certainly made strides, offered some, incremental automation, they faced critical technical limitations that ultimately prevented a truly streamlined pipeline.
Okay.
First, when it came to in-betweening, previous approaches often struggled significantly with large motions.
Big movements.
Yeah, if a character had a big sweeping movement, say a dramatic leap, or a complex spin interpolating that smoothly and coherently from just a few sparse sketch inputs proved really challenging.
So the AI couldn't figure it out.
Pretty much. These models frequently required artists to provide multiple intermediate keyframes for even a single smooth motion just to avoid jarring transitions or characters appearing distorted.
So the artist still had to draw a lot.
Exactly. They still had to draw a significant portion of those in-between keyframes, which heavily undermined the promise of automation.
Yeah.
The AI couldn't reliably fill in those large, complex gaps on its own.
That sounds like a frustrating compromise, not really automating the hard part.
It absolutely was. It felt like partial automation rather than a true offloading of the burden. And then for colorization methods, the recurring issue was the demand for dense input.
Dense input, meaning?
Meaning these models typically require detailed per-frame sketches. So even if the coloring process itself was automated by the AI, the artist still had to provide a complete, cleaned-up line art sketch for every single frame.
Every frame, wait.
Hundreds or even thousands of frames. So while it offered some automation for the coloring step itself, it still imposed a significant upfront workload on the artists for the line art. It was less of a revolutionary change and more, an incremental improvement to just one part of the overall bottleneck.
And here's where it gets truly interesting, technically. You mentioned something about sequential processing leading to error accumulation. From a technical standpoint, what exactly about this sequential processing in prior methods made them so prone to error accumulation, and why was it such a difficult problem to solve?
That's an excellent question, and it really highlights a core technical challenge that ToonComposer tackles directly. Imagine the traditional workflow, even with previous AI assistants, as a kind of multi-stage assembly line.
Okay.
First, you might have one AI model specifically trained for in-betweening. It generates all the intermediate sketches based on your keyframes. Then the output of that model, those newly generated sketches, gets fed directly as input into a second AI model, which is responsible solely for colorization.
Stage 1, then stage 2.
Exactly. That's what we mean by sequential processing.
Yeah.
One stage completes, its output becomes the input for the next. The fundamental problem here is that any inaccuracies or subtle artifacts introduced in an earlier stage directly propagate, and worse, compound in later stages.
So mistakes get amplified.
Precisely. For instance, if the in-betweening model makes a minor error in an interpolated sketch, maybe a character's arm is slightly bent unnaturally in one frame, or a line is a bit wobbly.
Little things.
Yeah, little things. But that error isn't corrected down the line. Instead, the colorization model receives that slightly flawed sketch and proceeds to color it as is.
Oh, I see.
So an interpolation error from the first model can directly affect how colors are applied, leading to visible issues. You might see shimmering lines as the sketch wobbles, or flickering colors as the model struggles to maintain consistency over an imperfect base. Characters whose appearances subtly shift from frame to frame.
Even if the sketch flaw was tiny.
Right. Even if the underlying sketch got only minor imperfections. It's like that game of telephone, but with visual information. By the time it gets to the end, the message is visibly garbled.
So the mistakes just build on each other, becoming more obvious and harder to fix as you go along. And you said this was a particularly difficult problem to solve. Why was that?
Well, it was difficult because these stages, while clearly related parts of the animation process, were often developed and optimized independently. Each AI model was a specialist. One for sketches, one for color.
Right.
They had their own internal biases, their own ways of interpreting data, their own inherent limitations. Building a single model that could simultaneously understand motion and color and seamlessly integrate them from sparse input. That was a significant architectural and training challenge.
A unified approach was needed.
Exactly. It requires a model that can maintain coherence and consistency across both spatial details, what things look like within a single frame, and temporal flow, how things change and move across frames, all within a unified latent space.
The model's internal representation.
Yes, essentially the model's internal, compressed, abstract, numerical representation of all the visual data. Older architectures weren't inherently designed to handle this unified understanding efficiently without losing fidelity or introducing new artifacts. It's not just about chaining two existing models together, it's about redesigning the fundamental approach to avoid that compounding error from the ground up.
Okay.
It needed a model that sees the animation as a cohesive whole right from the start.
That explanation really clarifies why this sequential approach was such a persistent bottleneck. And that brings us perfectly to ToonComposer's core innovation, the post-keyframing stage. This sounds like it directly addresses that fundamental problem of error accumulation. Tell us about this foundational solution.
This is indeed where ToonComposer introduces its central novel paradigm, the post-keyframing stage. Instead of separate sequential processes for inbetweening and colorization, ToonComposer merges them into a single, unified, automated process.
One step.
One step. In essence, this means that given just a few artist-provided keyframe sketches and a single colored reference frame, the model directly produces a complete high-quality cartoon video. It's no longer sketching first, then coloring.
Wow.
It's generating the full, colored video directly in one coherent step.
That's a truly significant architectural shift. What's the technical reasoning behind this unification? What makes these two seemingly distinct tasks, generating intermediate sketches and then coloring them, suitable for a combined approach within a single model?
The reasoning is actually quite elegant when you break it down. Both inbetweening and colorization, at their core, intrinsically involve finding correspondences and interpolating along them.
Similar processes underneath.
Very similar. For inbetweening, you're interpolating between the forms, positions, and expressions defined by those keyframe sketches. For colorization, you're interpolating color, shading, and style from a reference frame across the entire sequence of motion. Their underlying internal mechanisms are, in fact, remarkably similar. They both require the model to understand visual consistency and how elements evolve over time and space. Merging them allows the model to jointly utilize both the elementary structural information from the keyframe sketches and the style and color information from the reference frames, all within one coherent generative stage.
So it builds a holistic view.
Precisely. The model builds a holistic understanding of the entire animation sequence in its latent space, optimizing for both form and color simultaneously. And the immediate, most significant benefit of this unified approach: it completely eliminates cross-stage error accumulation.
No more telephone game.
Exactly. There's no handing off potentially flawed output from one AI to another. The model learns to produce a high-quality, artifact-free output directly from the original sparse input.
And the input is sparse.
Radically sparse compared to older methods. It only requires a few keyframe sketches and a single colored reference frame to generate a complete, high-quality cartoon video. This is a massive departure from needing dense per-frame sketches.
That's a huge reduction in workload.
It really is. It's a game changer.
So artists can now pour all their creative energy into designing those perfect, expressive keyframes, making the crucial artistic choices, and then essentially hand off the repetitive grunt work of filling in frames and coloring to the AI.
That's the vision, yes. It allows them to offload that repetitive work.
That really does sound like a profound shift in the animation workflow.
Absolutely. It redefines the artist's role in the pipeline, freeing them from the most monotonous, repetitive aspects and allowing them to focus on the higher-level creative decisions, character performance, story.
The art, not just the craft.
Exactly. Now, to achieve this ambitious unification and leverage the latest in generative AI, ToonComposer is built upon modern Diffusion Transformer, DIT-based video foundation models.
DITs, okay,
Yeah.
powerful stuff.
Very powerful. Think of DITs as highly advanced neural networks, using attention mechanisms to process information. They're particularly good for generating high-quality video because they can learn complex relationships within and across frames simultaneously. ToonComposer specifically cites its foundation on 1.2.1, known for superior video generation performance in naturalistic settings.
But adapting these for cartoons wasn't simple.
Not straightforward, no.
Yeah.
Integrating these powerful DIT models into the cartoon animation workflow brought two significant technical challenges that the ToonComposer team had to ingeniously overcome.
Okay, what were those specific hurdles?
The first was controllability. DIT models, while great for generating video from general prompts, are usually weakly conditioned, meaning they might be guided by a general text prompt like a person walking or maybe an initial frame, but they lack the precise, fine-grained control needed to guide motion, using sparse keyframe sketches placed at very specific temporal locations.
Like arm here at frame 10.
Exactly. You need to tell it not just generate a video of a person walking, but generate a video where the character's arm is exactly here at frame 10 and exactly there in frame 25. That level of precise, sparse, temporally aware control isn't natively built into standard DITs.
Got it. And the second challenge?
The second challenge was domain adaptation. DIT models are typically trained on vast data sets of natural videos, real-world footage.
Right.
So their internal representations are optimized for that kind of visual aesthetic. Complex textures, subtle lighting, realistic physics.
Right.
To produce high-quality cartoon videos with their distinct aesthetic, flat colors, clean lines, stylized forms, these models needed to be tailored.
Adapted to the cartoon style.
Yes, and this is where it gets technically tricky.
Hmm.
A DIT's full attention mechanism jointly learns both spatial behaviors, what objects look like within a frame, and temporal behaviors, how objects move and change across frames.
They're learned together.
They're intertwined. This meant that previous, simpler, spatial-only adaptation methods, designed for older U-Net-based models where spatial and temporal layers were more separate, were simply ineffective. You can't just tweak the spatial part of a DIT without inadvertently messing up the temporal part.
That's a fascinating problem. Given that DIT models are so powerful for natural video, what does it mean for their internal representation to have spatial and temporal behaviors intertwine, and why does that make adapting them to a new visual style, like cartoons, so much harder than with older model architectures?
That's an excellent question to dig into because it really highlights a fundamental difference in how these architectures process information. In older U-Net-based diffusion models for video, you often had, let's say, somewhat separate computational blocks.
Okay.
One set of layers might primarily focus on understanding spatial information within each frame, identifying objects, textures, colors. Another set would then focus on temporal information across frames, how things move, change, relate in time.
So you could target them separately.
Conceptually, yes. You could try to adapt the spatial layers to a new domain, like cartoons make lines sharper, colors flatter, without heavily impacting the temporal layers. You could largely preserve the learned motion dynamics.
Makes sense. But DITs are different.
Very different. DIT models, leveraging their transformer architectures, employ full attention mechanisms. This means within a single attention block, the model is simultaneously computing relationships between every token. A token being a fundamental unit of info, maybe representing a small patch of space within a frame, or the same patch across different frames.
So it's looking everywhere at once.
Pretty much. When a DIT processes information, it's not looking at spatial features and temporal features in isolation. It's looking at how a pixel at location, xy, in frame 1 relates to a pixel at xy in frame 1, and how that same pixel at xy in frame 1 relates to a pixel at xy in frame 5, and how it relates to xy in frame 5 all at once within the same attention calculation.
Wow. Okay, that sounds complex.
It is. And this intertwined nature makes them incredibly powerful for capturing complex, long-range dependencies in natural video. That leads to very smooth, coherent generations.
but bad for adaptation.
It creates a significant challenge for domain adaptation, yes. If you try to adapt only the spatial aspects, say, making lines thicker or faces more stylized, typical cartoon stuff, you're modifying a system where spatial and temporal understanding are deeply coupled.
Right, you might break the motion part.
Exactly. Any change to the spatial representation can inadvertently perturb the carefully learned temporal prior, the model's inherent understanding of how things naturally move. This can lead to undesirable flickering, inconsistent motion, or other temporal artifacts.
Like adjusting the bass on a stereo and messing up the treble.
That's a great analogy. It's like the bass knob also subtly changes the treble and volume simultaneously. You need a much more nuanced, targeted adaptation approach that can influence the spatial aesthetics without destabilizing the rich temporal understanding the model already has.
That analogy helps immensely. It truly sounds like delicate surgery to adapt these models. So now that we understand the intricate problems ToonComposer faced, let's talk about the specific technical innovations. How does it work under the hood? Let's start with that sparse sketch injection mechanism.
Right, the sparse sketch injection mechanism. This is one of ToonComposer's really ingenious solutions, specifically designed to enable that precise control over generation using those sparse keyframe sketches placed at arbitrary temporal positions.
Guiding the AI with minimal input.
Exactly. Its core purpose is to guide the generative process with minimal yet powerful input from the artist. So here's the technical breakdown. First, ToonComposer introduces an additional projection head.
Okay, a new component.
Yes. What this does is take your conditional sketch latents, basically, the compressed numerical representation of your input sketch, it's DNA and AI language, and embeds them into what are called sketch tokens.
Sketch tokens.
Right. And these sketch tokens are meticulously designed to be compatible with the Diffusion Transformer model's latent dimension. Think of the latent dimension as the specific numerical format or dialect the DIT uses internally for all its data, video, or prompts.
So it translates the sketch into the DIT's language.
Precisely. It makes the sketch tokens speak the same language so they can be seamlessly integrated into the DIT's existing data flow without loss in translation.
But it needs to know when to apply it too, right?
Absolutely crucial. It's not just about what the sketch looks like. The model needs to know when in the video sequence that sketch information should apply. This is achieved through position encoding mapping.
How does that work?
ToonComposer uses something called ROPE, or rotary position embedding, encodings. Think of these ROPE encodings as highly sophisticated digital timestamps and location markers. They're specifically drawn from the corresponding video tokens at the exact temporal index, say, frame 10 or frame 25, where the artist wants the sketch to apply.
So the sketch token gets a timestamp.
Essentially, yes. This temporal awareness is integrated directly into the sketch tokens before they even enter each attention operator within the DIT. So when the model processes a sketch token, it inherently knows not just what it looks like, but when the video sequence, it should apply that information with pinpoint accuracy.
And then these tokens join the main data stream.
Exactly. These sparse sketch tokens are then concatenated with the video tokens along the sequence dimension. They're added directly into the stream of data that the DIT's attention mechanism processes. This allows the model to attend to both the evolving video content and the guiding sketch information simultaneously.
Enabling that precise temporal control.
That's the goal. And a critical aspect here is its flexibility. It supports using multiple keyframes and sketches as control input.
Which is needed for complex scenes.
Absolutely crucial for complex motions, where a simple start and end sketch just isn't enough. If you have intricate character movements, nonlinear paths, you might need more control points. ToonComposer lets artists add these at any temporal location.
But it still works with minimal input, too.
Yes. Importantly, it also maintains the ability to work with truly minimal input, as few as one colored reference frame and just one sketch frame, delivering on that core promise of dramatically reducing manual workload while still getting high-quality results.
That's a thoughtful and robust design, both control and flexibility. And you mentioned a position-aware residual that gives artists even more dynamic control. What's that about?
Yes, that's a really valuable feature for animators. The position-aware residual lets users dynamically adjust the control strength of the input sketches during the inference stage, when the model is actually generating the animation.
Adjusting the sketch's influence.
Exactly. This is done through a trainable linear layer called res and a scaling weight named alpha. During training, alpha is fixed, usually at 1, but during inference, the user can manually dial this alpha weight up or down.
The alpha scaling weight for sketch control is fascinating. What does its existence imply about the model's confidence or flexibility in adhering to the sketch versus its own learned temporal priors? How might an artist leverage this knob in practice, thinking about their day-to-day workflow?
That's a truly insightful question. It points to a very sophisticated interaction within the model. The existence of that alpha scaling weight implies a deep understanding within the model about its own internal state and how it interacts with external human guidance.
A balancing act.
It is. On one hand, the DRET model has these powerful temporal priors. It's learned from vast amounts of video how things naturally move and change over time. It has an inherent learned grasp of motion continuity, basic physics, how characters typically deform.
Its own knowledge, right?
On the other hand, the input sketch provides explicit, precise human-intended guidance. Make the arm look exactly like this at this moment.
Got it.
The alpha knob is the artist's way to balance these two crucial sources of information. A higher alpha tells the model, trust this sketch implicitly, even if it slightly conflicts with your default natural motion understanding. Less flexibility maybe, but higher precision to the artist's intent.
More rigid control.
Exactly. Concurrently, a lower alpha suggests, use this sketch as a general guide, but feel free to lean more on your learned temporal priors to create a smoother, more natural-looking animation if the sketch is rough or incomplete or might lead to janky motion.
More flexibility for the AI.
Right. More willingness to interpolate based on its internal knowledge. In practice, an artist could use this constantly. For a very precise, critical P-frame, a unique gesture, a complex expression, they might crank up alpha.
Make it stick perfectly.
Yes. But for a background element or a secondary character's movement that doesn't need pixel-perfect adherence, or maybe just a quick, rough guide sketch, they might lower alpha.
Let the AI smooth it out.
Exactly. Let the model fill in the blanks more creatively, ensure overall motion smoothness, prevent overfitting to minor imperfections in a rough sketch. It gives the artist this subtle but powerful fidelity to input dial.
That's incredibly powerful for an artist, giving them fine-grained control over the AI's interpretation. Now, let's talk about the other big technical challenge: adapting these powerful DITs trained on natural videos to the distinct look of cartoons. How does the Spatial Low-Rank Adapter, or SLRA, solve this intricate problem?
Right, the Spatial Low-Rank Adapter, SLRA, it really is a brilliant piece of engineering, specifically designed to efficiently adapt the spatial appearance, the look of the DIT Foundation model, to the cartoon domain without disrupting its powerful temporal prior, its understanding of motion.
Avoiding that intertwined problem.
Exactly. As we discussed, the problem it solves is that intertwined nature of spatial and temporal representations in DITs, which made older adaptation methods ineffective. SLRA, much like its predecessor, traditional low-rank adaptation, uses that clever trick of introducing two small, trainable matrices, woe down and wup.
The LoRa concept.
Yes. It downsamples the input hidden token's feature dimension, reducing complexity,
Yeah.
but then upsamples it back. The magic is these small matrices learn the differences needed for adaptation, rather than retraining the whole huge model.
But SLRA adds something new.
Yes, here's the crucial distinction that makes SLRA so innovative for this specific problem. After downsampling, the hidden state is reshaped, not randomly, but specifically to explicitly recover its inherent spatial temporal arrangement. Then, and this is the key, a self-attention operation is performed only on the spatial dimension of each frame independently.
Only spatial, frame by frame.
Exactly.
Yeah.
It effectively isolates spatial adaptation. The model learns cartoon-specific visual characteristics, line style, color flatness, character proportions, shading style frame by frame. This learning happens without forcing these spatial changes to propagate across the temporal dimension during this specific adaptation step.
Keeping motion separate.
Right. And importantly, the main model's positional embeddings are still applied during this spatial-only attention, maintaining context for the larger model.
So it's like performing highly targeted surgery on the model. Instead of broadly adapting everything, which might mess with motion understanding, it targets only the visual style aspects, leaving motion dynamics largely undisturbed.
Precisely. That's a great way to put it. This design ensures cartoon-specific spatial features are learned and applied, while the underlying temporal coherence and powerful motion understanding from the base DIT remain intact. The output of this spatial-only adaptation, HRS, is then added as a residual back to the main DIT block's output.
So the cartoon style influences the final output.
Yes, it influences the main model's output without forcing the main model to relearn its sophisticated temporal understanding from scratch. It's highly efficient and effective for adapting large models to new domains without catastrophic forgetting or performance degradation in other areas.
And the paper backs this up.
Absolutely. The paper provides strong experimental validation through an ablation study. Standard practice in AI research where you systematically remove or alter components to see their individual contribution. They meticulously compared SLRA against several alternatives: temporal adaptation, spatial temporal adaptation, linear adaptation, even standard LoRa.
How did SLRA do?
The results, shown clearly in Table 4 and Figure 8 of the source material, unequivocally show SLRA outperforming all of them across various metrics.
That's compelling. Why did these alternatives fall short? What did the ablation study specifically reveal about SLRA's unique strength and how it tackles this intertwined spatial temporal problem?
Well, the study revealed that the alternatives either didn't provide sufficient or maybe even conflicting spatial adjustments, or they lacked nuanced adaptation, or crucially, they disrupted those critical temporal priors learned from natural video.
They broke the motion understanding.
Often, yes. For instance, temporal adaptation focused too much on motion, inadvertently neglecting the stylistic changes needed for cartoons. Spatial temporal adaptation tried adjusting both, but without SLRA's precise isolation, leading to less optimal results, often introducing visual artifacts.
And the simpler ones?
Linear adaptation was just too simplistic, lacking the expressive power for nuanced cartoon art. And even standard LoRa, while effective elsewhere, underperformed here because its broader scope implicitly alters both spatial and temporal behaviors without the same surgical precision.
So it wasn't targeted enough.
Exactly. It's less targeted, which, for this specific problem where temporal coherence is paramount, proved detrimental. SLRA's targeted approach won because it understands exactly where to apply stylistic changes, spatially, frame by frame, without breaking the foundational motion understanding the DIT it already mastered.
This SLRA truly is a brilliant piece of engineering, a very clever solution. I'm curious, how might a future researcher try to invert this process to understand precisely what spatial features it's learning for cartoon aesthetics? Are there ways to visualize or quantify the cartoon domain that the SLRA is adapting to, almost like creating a cartoonness score?
That's a fascinating area for future research, yeah. Moving beyond just performance metrics to truly understanding what the model has learned. Inverting the process, or maybe more accurately, interpreting the learned representations within SLRA could involve a few cutting-edge approaches.
Like feature visualization.
Exactly. Techniques similar to feature visualization or concept activation vectors, CAVs, used in other deep learning interpretability contexts. Researchers could try to identify specific neurons or activation patterns within SLRA's trained one-bond and WUP matrices that respond strongly to certain cartoon characteristics.
Finding the thick outline neuron.
Kind of, yeah. By feeding in diverse cartoon images, then systematically manipulating activations within SLRA, they might generate synthetic images, emphasizing specific elements, thicker outlines, simplified textures, characteristic facial features. It could reveal which knobs within the adapter correspond to specific stylistic attributes like anime eyes versus Western cartoon eyes.
What else?
Another approach could be using saliency maps or adversarial perturbations. Observing which parts of an image cause SLRA to activate most strongly, or which minimal changes push a non-cartoon image closer to the cartoon domain, as interpreted by SLRA, that could help build a quantitative definition.
Defining cartoon-like.
Potentially.
Yeah.
You could also use other models, like training an auxiliary model to discriminate between natural and cartoon frames, then analyzing what features that model relies on, maybe cross-referencing with SLRA's internal features.
Kind of quantifying it, a cartoonness score.
That's even more complex, but highly intriguing. One can imagine defining a cartoonness score based on SLRA's internal states or output, like run natural video frames through the adapted SLRA. How much cartoon signal does it generate? How does that change with different cartoon styles? It could lead to a numerical representation of an image's adherence to the cartoon aesthetic, as understood by the model. It's an exciting frontier for explainable AI in creative domains.
Absolutely. Moving beyond it works to how and what does it understand.
Right. That's brilliant. Okay, let's look at one more technical innovation that seems to directly impact the artist's day-to-day workflow. Region-wise control. This sounds like it could be a massive time saver.
Indeed, region-wise control is all about further alleviating the artist's workload. It allows flexible motion generation without the artist having to meticulously draw sketches in every indicated region of the frame.
So you can leave parts blank. Exactly. The problem it solves is practical and common.
Right.
Artists might only want to sketch foreground elements, like a moving character, while intentionally leaving the background blank. Maybe they expect the AI to generate it, or it's a static background they'll add later.
And without this control.
Without this specific control, the model would misinterpret those blank areas in the input sketch as genuinely textureless or empty regions. This leads to flat, undesirable artifacts or misinterpretations. Figure 9 in the source material shows this well. A blank train background becomes just flat blue, lacking detail.
Okay, so how does it fix that?
To avoid this, ToonComposer uses a clever technical mechanism. During training, random masks are applied to sketch frames. These masks essentially tell the model, hey, this specific area of the sketch is not provided. It's intentionally blank.
An extra signal.
Yes. An additional channel, encoding this mask information, is then concatenated to the sketch input. So the model receives not just the sketch lines, but also a precise map saying, this part is intentionally empty. Don't interpret it as blank space. Interpret it as an area where you should generate plausible content.
So the model learns that a blank area, when accompanied by this mask channel, means you fill this in creatively based on context and your learned priors, rather than this area should literally be empty or featureless. That's a significant distinction.
Exactly. This allows the model to learn to reconstruct full frames in these mask regions, generating plausible content based on the context of the surrounding sketch, other reference frames, maybe even text prompts. The example in Figure 9 is striking. You see a dynamic train movement intelligently filled in by the model, details and textures included, even though the artist only sketched the foreground character.
So artists just define the mask.
Pretty much. Users can simply define a masked area, and ToonComposer intelligently fills it in. This significantly reduces manual drawing effort, making input sketches spatially sparse. It dramatically improves efficiency and gives artists more creative freedom over what they need to draw themselves.
Focusing effort where it matters.
Right. It's another intelligent layer of automation built right into the core architecture, anticipating how artists actually want to work.
That's truly about empowering the artist, reducing the grunt work. Now, for any new AI model, especially one promising to revolutionize an industry, the proof is in the pudding: validation and performance. How was ToonComposer evaluated, and what did the empirical evidence show?
This is where we see the real-world impact. First, the data. For training, the researchers curated a large-scale, high-quality cartoon dataset called PKData. Impressive stuff. 37,000 diverse cartoon video clips.
Wow.
And crucially, to improve robustness to real-world sketch variations, because artists have different styles, use different tools, they augmented the data with multiple sketch styles per frame.
Not just one type of sketch.
No. Basic line art models, but also specialized ones like Anime 2 Sketch, Anyline, and a new one called Icy Sketcher, which generated sketches from multiple human artists. This diversity helps ensure ToonComposer isn't brittle when faced with an artist's unique style or an imperfect sketch.
Smart. And for evaluation?
For evaluation, they developed PKBench, a novel benchmark designed for realistic scenarios. This isn't just synthetic data. It features 30 original cartoon scenes with actual human-drawn keyframe sketches.
Human-drawn, that's key.
Vital. It accurately simulates real-world use cases, providing a much more realistic and challenging evaluation than just using clean machine-generated data. It tests how the model handles actual artist input.
That's a smart move. It's one thing for AI to work on perfect inputs, but the real test is handling an actual artist's varied work. What about the metrics? Just pixel comparisons?
Oh, they used a really comprehensive set of evaluation metrics to capture various aspects of video quality. For the synthetic benchmark with ground truth references, they used reference-based perceptual metrics like LPIPS, DISTs, and CIIP image similarity.
Metrics that mimic human perception.
Exactly. LPIPS and DISTs measure perceptual distance, how similar images look to a human eye. CLIP similarity assesses semantic similarity, how close the meaning or content is.
And for the real benchmark, without ground truth?
For both synthetic and real benchmarks, they strategically used reference-free video quality metrics from a robust framework called VBench. These assess inherent qualities of the generated video itself, things like subject consistency: do characters maintain identity? Motion consistency: is movement smooth, no flickering? Background consistency: is the environment stable? And aesthetic quality: the overall visual appeal.
A broad assessment.
Very. And most importantly, recognizing animation as art judged by humans, they performed a user study on the real-world PKBench. Actual users rated their aesthetic and motion quality preferences for videos from ToonComposer versus others.
Human perception is the ultimate judge.
Absolutely. Quantitative metrics are vital, but human perception is the final arbiter in creative fields.
So, after all that rigorous testing, how did ToonComposer stack up against the existing methods like Anadoc, LVCD, ToonCrafter? Did it really deliver?
The results were demonstrably superior
Yeah.
across the board. Looking at the quantitative evidence, Table 1 for synthetic, Table 2 for real ToonComposer consistently outperformed previous methods across all metrics.
Significantly better.
Yes, significantly lower DS scores, meaning much better perceptual quality, higher CLIP similarity, so semantically closer outputs. On VBench metrics, its subject, motion, and background consistency scores were notably higher, as was overall aesthetic quality. These weren't marginal gains, often substantial improvements, indicating a real leap in capability.
And qualitatively, could you see the difference?
Oh, definitely. The qualitative comparisons, which you can see visually in Figures 6 and 7 from the paper, powerfully reinforce the numbers. ToonComposer produced consistently smooth and natural cartoon videos. High visual quality, motion coherence, style consistency throughout.
And the older methods?
In stark contrast, older methods often showed issues like distorted faces warping over time, lost details and critical character elements, inconsistent styles that flickered or changed unnaturally. Figure 7 specifically highlights how ToonCrafter may be overly influenced by bold human brushstrokes in its training, generated prominent, thick lines in intermediate frames where they weren't intended.
Showing limited robustness.
Exactly. ToonComposer, on the other hand, maintained a consistent, high-quality style, demonstrating its superior understanding of the cartoon aesthetic.
And the user study, what did people prefer?
The user study results in Table 3 are particularly compelling. ToonComposer achieved a dramatically higher user preference rate for both aesthetic quality, an impressive 70.99%, and motion quality, 68.58%, far exceeding competitors.
Wow, that's decisive.
It really is. That's perhaps the most powerful validation that human observers consistently prefer ToonComposer's output, recognizing its superior quality and fluidity.
That's incredibly strong validation from both objective metrics and human perception. Looking at these improvements, what does it tell us about the power of integrating these stages inbetweening and colorization versus the traditional sequential approach? And maybe a broader question, is there a theoretical limit to how much manual labor AI can realistically absorb in creative processes like animation?
Well, the overwhelming success of ToonComposer's integrated approach strongly suggests that for tasks like inbetweening and colorization, where both rely heavily on understanding correspondence and interpolation across frames and elements, treating them as a single unified generative problem is fundamentally more effective.
The whole is greater than the sum of its parts.
In this case, yes. When combined in one model, it develops a holistic understanding, predicting movement and final styled appearance simultaneously. This prevents error propagation, ensures greater consistency, and allows for more fluid, high-fidelity output because the knowledge of motion and appearance is shared and optimized together from the start. It's optimizing for the entire visual flow.
Makes sense. And the limit to AI absorbing manual labor?
That's a profound question we're just starting to explore. If we define manual labor in animation as highly repetitive, rule-based, or interpolative tasks, generating frames between keys, filling colors consistently, maybe basic rigging, then the current trajectory suggests AI can absorb a very significant portion, maybe close to 100% of those specific mechanical tasks.
So the limit is elsewhere.
The limit might shift to where truly creative decision-making begins and ends. AI can automate the how to move smoothly, how to color consistently, but the what and why, what key poses convey emotion, what narrative beat they represent, what comedic timing is needed, the overall emotional impact, these currently remain firmly human.
The artistic intent.
Right. The theoretical limit might be where the task requires truly novel, non-interpolative creative leaps, abstract conceptualization, or deep emotional and contextual understanding beyond statistical patterns. ToonComposer moves the boundary, pushing AI much further into the how to draw an animated space. But the what to draw and why draw it this way still seems human. It's about automating the craft, maybe not the art itself.
That makes a lot of sense. It really elevates the human artist, freeing them from mechanics to focus on higher-level creative ideation. Before we wrap up this deep dive, let's discuss some broader implications and some of the unseen questions this technology raises.
Absolutely. One exciting broader implication is ToonComposer's remarkable versatility. The paper briefly but importantly mentions its successful fine-tuning for 3D rendered animation.
3D, that's significant.
Incredibly significant. 3D animation has its own complex, labor-intensive pipeline. ToonComposer, adapting to it, highlights the robustness and generality of its core innovations, like sparse sketch injection and SLRA. It suggests they're powerful enough for different visual styles and data structures beyond just traditional 2D.
So it could be a general tool for digital content.
Potentially a very powerful general-purpose tool, yes. Revolutionizing many areas, not just cartoons.
That's a huge leap. If it can adapt to 3D, it opens up so many possibilities: games, VR, not just film, TV. But the paper does briefly mention computational costs as a limitation. That makes me wonder about practical deployment. What does this imply about the hardware demands? And what other technical considerations might be crucial for real-world use, like inference speed, model size, fine-tuning accessibility for smaller studios or individuals?
That's an excellent point. The practicalities of real-world deployment are often the silent challenge. Mentioning computational cost for a model like ToonComposer, built on large DITs like 1, 2.1, generally implies substantial hardware demands.
High-end GPUs.
Definitely. High-end GPUs, likely multiple, with lots of VRAM, powerful workstations, or robust cloud infrastructure. Training would need supercomputer-level setups. Inference generating animation, while less demanding, producing even a few seconds of high-res, high-quality animation smoothly, would still likely require dedicated GPU resources.
A barrier for some.
It could potentially bottleneck smaller studios or individual artists without access to powerful machines or significant cloud credits. And beyond raw hardware, there are other crucial considerations, often less detailed in research papers.
Like speed.
Inference speed is paramount.
Yeah.
How long does it actually take to generate a 30-second clip at production quality? If it's hours, even on top GPUs, it might not be practical for rapid iteration. Artists need quick feedback.
And model size.
Model size impacts storage, transfer, accessibility, especially with limited bandwidth. Can it run locally, or does it always need the cloud?
And fine-tuning.
Fine-tuning accessibility. How easy is it for individual artists to fine-tune it for their specific style? Does it need massive curated data, or can it adapt quickly from a few examples? What are the costs of that fine-tuning? These are the deployment-level engineering questions that follow breakthroughs and determine real-world impact.
So even with such a powerful tool, getting it into every animator's hands ubiquitously might still be a significant engineering challenge. Which leads to this. If the mundane, repetitive tasks, the grunt work, are largely automated, what new creative frontiers might open up for animators or concept artists? How might their role fundamentally transform?
If the drudgery of inbetweening and colorization is largely automated, the animator's role could shift fundamentally, from being a highly skilled laborer focused on execution to a master of conceptual design, expressive direction, and rapid iteration.
More focus on ideas.
Exactly. Animators might spend way more time on storyboarding, developing dynamic, imaginative key poses, experimenting with complex camera moves, cinematic angles, exploring diverse character designs or visual styles.
Faster prototyping.
Much faster. They could iterate on creative ideas rapidly, test multiple motion styles for a scene without immense effort, maybe even branch into entirely new forms of interactive animation or immersive experiences previously too labor-intensive or costly.
So the focus shifts from execution to intent.
Dramatically. It moves from meticulously executing frames to purely focusing on imaginative vision and overarching artistic intent. It's about unlocking a new era where creators are free from the mechanical aspects to concentrate on pure imagination, conceptual design, emotional storytelling. It enables more ambitious, experimental projects.
What an exciting thought to end on. ToonComposer is truly a testament to engineering brilliance, unifying inbetweening and colorization into that powerful post-keyframing stage. The sparse sketch injection, coupled with that clever spatial low-rank adapter for precise domain adaptation, it's clearly revolutionizing how cartoons and anime can be produced. Faster, more efficient, high quality, a remarkable piece of technical innovation.
Indeed. It's a very exciting development in AI-assisted creative work, really pushing the boundaries of what's possible in animation.
So as AI continues to refine and automate these laborious, almost mechanical aspects of creative production, what does it truly mean for human artistry? Is AI enabling a new era where creators are freed from the drudgery of in-betweening to focus purely on imaginative vision and conceptual design? Or does it fundamentally alter the very nature of what it means to draw a cartoon? It's a question that will continue to evolve, and one we'll certainly keep exploring here. Thank you for joining us on this deep dive.